Okay, hello everyone. I am your first lecturer for today, and let's do some algebra. And in particular, we will focus on the topic of functional equations. So first of all, anyone doesn't know what functional equations are? And by the way, you may use your chat box, and if you are shy or anything, you can probably message me in private if that feature's available, which I think it is. So just to check if everyone's here, just type something in the chat, either in private or in public. Okay, nice. So let's start. Anyone not familiar with functional equations? Okay, so no one. So everyone has some basic understanding of functional equations, which is great. And before we move on to the techniques, which you can find in your handout. In fact, I should probably send the handout here as well. Give me a moment. Okay, there it is. So before I move on to the techniques, let's just have a study on a particular type of functional equation, which is Cauchy's equation. And afterwards, we will kind of introduce some stuff after that. So first of all, Cauchy's equation, we will look at the easy. Let's look at the easiest version first. So that will be fx plus y equals fx plus fy. So such a function is normally called linear, where x and y are integers. And also f is from z to z. So anyone has any idea? Okay, for those who know, you can just private chat me, because we don't want to spoil the answer to everyone. So anyone knows what the answer for? Yes, exactly. And in fact, this is an easy version, so I just spoiled the answer. So fx would be cx for some constant c, and for every x in in z. And why is that? So first of all, we can see obviously f0 is 0 by substituting x and y at 0. So the main thing is, if I let f1 be c, I define this to be c. The thing is, this equation can be transformed into a multivariable version. So x1 plus x2 plus dot 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 plus xn equals fx1 plus blah 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 plus fxn. And why is that? You can just pick y to be y plus z, and then you have a y plus z term over here, and then you repeatedly use that argument, so you can generalize to n variables instead of 2. And if that's the case, then f1 plus 1 plus dot 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 plus 1 would be f1 plus dot 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 plus f1, and there are n terms. So you can see that fn would be f1 times n. But of course, this is for the positive integers. And how do we get the negative integers? Yeah, you can sub 1 and minus 1. So if you sub 1 and minus 1 to the first equation, in fact, for functional equations, I sometimes like to, let's say, let this statement be pxy. Then here what we're doing is, let's say we plug in 1 and minus 1. Then we get f0 on the left, which is 0, equals f1 plus f minus 1. So f minus 1 is minus c. And then you can apply the same thing again. Minus 1, minus 1, minus 1. So you get f minus n is f1. Like this. So in fact, yes, so fx is cx, where c is any integer. Okay, so this is the easiest version of Cauchy's functional equation. Now let's step up a bit and look at the rational version. So the rational numbers version. So the same equation, but now I allow the domain to be the set of rational numbers, and I allow the image or range or codomain to be the rational numbers as well. Then, well, this argument still works, right? So f1, let's say, is equals to c, then fn equals f1n, f minus n is n times my negative f1. So the first part is okay. The first part is the same. We get that. So what if? So first part is the same. We get fn is equals to cn for all integers n. But now we have a relaxed condition for c. In the previous version, c is required to be an integer, right? And now it's allowed to be any rational number. So c is some rational number. Okay. And it makes sense, right? It's consistent with the previous one. Now, how do we move on to the quotients of integers? So how do we get f1 over 2, for example? How do we get f1 over 2? Any ideas? fp over q. Yes, that so someone said fp over q is p f1 over q, which is correct. But now we have to know what this is in order for this equation to be useful, right? So how do we get, let's say, q equals to f1 half? Well, how do we get 1 half? F0 plus 1 half. Okay, but if we put let's say we put 0 as x, y as half, we get the same thing on both sides, right? So we don't extract any information from that substitution. And yes, someone said, because we take this equation, notice how on the left hand side we have x plus y, and on the right hand side we have x and then y separately. But we know 1 half plus 1 half is an integer, right? It's equals to 1. So if we plug in 1 half, 1 half, we get f1 equals f half plus f half, and f1 is c, so f1 half equals c over 2. And yes, so we can generalize this. So how do we get f1 over n? We just use the generalized form of the equation, right? In fact, I can let this be qx1, x2, xn, but I'll just, well, you should get the idea. So we have f1n, 1 over n plus dot 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 plus 1 over n equals f1 over n plus dot 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 plus f1 over n. And this is f1, which is c. And this is n times f1 over n. So f1 over n is c over n. Yep. And of course, now we have f1 over n. We can get fm over n. And how do we do that? Oh yeah, by the way, a minor detail. Of course, n here must be a positive integer. It doesn't make sense if it's a negative integer, because I cannot add this minus 10 times. But of course, if it's negative, I can just use the x and minus x argument again. So that's a minor detail. So this should be n equals 1, 2, 3, 4. But for the negatives, you can just do it yourself. So fm over n, let's say m is positive. So now we can utilize this generalized form again, because we now know what 1 over n is. And this equation tells us we can just repeatedly plug in 1 over n, let's say m times. So we can get fm over n easily. So this is, well, I should probably mention this is n times, this is n times, and this is of course this is m times 1 over n dot dot 1 over n. And there are m terms here. So this would be m times of c over n, and hence c m over n. And then do the same for the negatives, so we can conclude that fx is cx for all x rational. So yeah, still not a very difficult problem if we level up the domain and codomain to Q. But the thing is, we get into trouble when we want to extend this concept to real numbers, because in this equation we manage to access every single rational number by just repeatedly doing addition or multiplication and division by integers, right? So we can access all the rational numbers in this way by just studying the integers. But the thing is, what if we have f pi, for example? We cannot really access pi, we cannot really reach pi by combining integers via addition, subtraction, multiplication, and division, right? So here's the trouble. So how do we get f pi? And so here's what we're going to study. And of course, there are a few conditions that allow us to say f pi is c pi. So our guess, the very reasonable guess, of course, is that fx, is if f is from R to R instead. The very reasonable guess is reasonable guess is fx equals cx, right? For all, for all x is real, and then we say c is a real constant now. And someone asked, do we just define f pi to be something new? Yes and no, and we will take a look at what conditions allow us to do that. So in fact, this guess it turns out to be not very correct. You must have some backup supporting condition for you to conclude this. So for example, the very easy condition, if you know it, is what if f is continuous? So what if f is continuous? Of course, in most cases, we don't even know if it's continuous, but let's say it's continuous. Then can we conclude from fx equals cx for x rational to fx equals cx for x is a real number? Can we do that? So what do we mean by continuous? Anyone has an idea what continuous means? In fact, there are many equivalent definitions. Well, formal definitions. But you can give an informal one if you like. The whole function is defined. Not really. And every function is defined in some way. So what makes a function special when it's continuous? F is continuous at a if fa equals limit of x going to a. Yeah, that's one of the definitions. So someone said f is continuous at a if x goes to a. If limit of x going to a of fx is fa. Okay, so everyone's there's a lot of definitions here. But everyone's definition is more or less something to do with limits, right? Something to do with limits, which is okay. And someone said, if you plot it out, it's connected in a line. Yes, that's an informal way of saying it. So if you graph the function, it will look like a very nice curve. Or it doesn't have to be very nice curve, it can be like that as well. But so this is a function that is continuous everywhere. And of course you can say a function is continuous at a single point. But let's just not look at that case. We just look at the case where f is continuous everywhere. So someone said the graph would be smooth. Yeah, kind of. So by smooth you mean they are connected. So even though there's like a kink here, we still say it's connected. But the definition I'll be using here, which is entirely equivalent if you've learned analysis, is this. So it's something to do with limits as well, but I phrase it in a non-limit kind of way. So if x1, x2, x3, dot, if this sequence is convergent, let's say to some number x, then fx1, fx2, dot, this sequence is also convergent to fx. So I'll use this definition of continuity. And this is one of the formal definitions you can prove. Someone asked, is this just epsilon delta phrased differently? Yes, it is. It is equivalent to the epsilon delta definition if you've learned it, which I don't require you to learn it, but you can if you want to. It is also equivalent to the limit definition. It is also equivalent to the Cauchy condition, if you know what that is. Is it called a Cauchy? Yeah, it's called a Cauchy sequence condition. But we're just going to use this definition. And why is this helpful? Because we know the answer for all rational numbers, right? We know the answer for all rational numbers. If we plot that out, it's gonna be a very empty but still not. It will look like a very connected but still very empty line, if that makes sense. Because Q is what we call dense in R. And what do I mean by dense? It says given any interval, there must be a rational number inside. So if we take the real line, for example, and we take, let's say, a very, very small interval, very small interval, however small it is, there is still a rational number inside. Does that make sense? So for example, is there a rational number between, I don't know, let's say pi and pi squared minus, oh, whatever. So not important anyway, but so let's just write it here. So right everywhere here. Let's say here. So Q is dense in R for any reals R1 less than R2. There is a rational number in R1, R2. So anyone knows how to prove this? It's more of a combinatorics question, but it will be useful. Well, if you want to use this one, it's also fine. R1, R2. Okay, so how do we prove this? Well, yes, someone said it. So it's basically pigeonhole. And well, one of the ways you can use is pigeonhole. Another way is, well, in the end, it's still in the end, it's still something about pigeonhole. So the thing is, R1, R2, if we subtract it, let's say this difference is D, right? Or let's say it's delta. Yeah, delta. Let's say the lowercase delta because it's small. So let's say this difference is delta. First, we can choose some rational number Q, which is whose absolute value is, okay, fine, some rational number Q between 0 and delta. Okay, so why can we do that? So however small this difference is, we can still find some rational number between 0 and that number. Well, we can just consider, let's say, 1 over n, and then we just make n to be very large, right? Because we know this sequence will go to 0. So we can, if we take n to be very large, then Q will be a very, very small rational number. And if we have that very, very small rational number, any multiple of it is still a rational number. But if we start from 0 and step ahead every second by q, eventually we must go into this interval, right? Because we've chosen this step length to be shorter than the interval itself. It cannot skip the interval. It must go into the interval somewhere. And this would be a rational number between R1 and R2. Does that make sense? If you're okay with it, say okay or something, because I'm worried if I explain it wrongly. Okay, so right. So most people got it. I assume all understand it now. So Q is dense in R. So how would we choose our sequence here? How would we choose our sequence here? So we'll do this. Let Q1, Q2, Q3, ... converge to some real number R. In fact, we should let R be any real number. Let R be any real number. So we first find some sequence that converge to that real number R. And why does it exist? We just consecutively use the density argument for the interval R minus epsilon, R plus epsilon or something. So a very, very small neighborhood of R, there must be a rational number inside. And if we just narrow this interval more and more, we will keep finding rational numbers inside. So if we just plug those rational numbers out, then this sequence will be convergent to R, if that makes sense. Well, the most straightforward way is to say, oh, real numbers can be written in decimal, right, as an infinite decimal. And then we just take the partial decimals, right? Let's say 3.14159, let's say pi. Then we just say 3.1, 3.14, 3.141, 3.1415, 3.1419. And this will be a sequence of rational numbers converging to pi. But anyway, I'm just explaining why this exists. So let this be convergent to R, then since f is continuous, fq1, which is cq1, fq2, which is cq2, fq3, which is cq3, this should converge to fr, right? But this sequence is just the previous sequence multiplied by c. So this must converge to cr as well. Therefore, fr is cr. And since r was arbitrary, fx equals cx for all x. So in conclusion, if f is known to be continuous, then fx can be cx. I mean, it must be cx for all real numbers x. So you cannot assign a new number to f pi anymore. F pi must be forced to be c times pi, for example. So another condition that I will treat very in detail is if f is, so case 2, if f is bounded from above or below on some interval AB, where A is less than B. So A and B are fixed. So what does it mean when I say bounded from above? It means there's some upper bound. So it won't exceed that number. And when you say bounded from below, it means there's a lower bound. It means you cannot go underneath that number. So for example, if this is the real number line and you have A and B, then you know the images or the range of all the numbers in this interval, irrational, rational included, they all lie in this strip. So they all lie between some upper bound and lower bound. In fact, some lower bound is enough because I say or here. It's not an and, it's an or. So if I know that every single image lies above this lower bound, then I can say fx equals cx. Very surprising result. So this kind of looks to me nothing to do with continuity, but apparently we can prove that fx equals cx from this condition. So either there is some lower bound or there is some upper bound on this interval. And how do we do that? This is a much harder case, but I hope everyone can learn something from this proof. So we will prove the contrapositive. So we will prove instead, or contradiction if you want. If FR is not equals to CR for some R, which is of course irrational because we already know fx equals cx for all rationals. So if FR is not equals to CR for some R, then F is unbounded above and below on any interval AB. So it's completely the opposite of what we're saying. We're just trying to prove by contradiction. I mean, well, you can call it contradiction or you can call it contrapositive if you want. So I assume the result is false. And then I prove that the premise, the assumption is false. So if FR is not equal to CR, then this condition would not hold. Okay, so how would we start doing this? It's a bit hard to visualize the function now because we kind of have this very solid line, but at the same time very empty because it skips all of the irrational numbers. But then for some R, it suddenly has some new number assigned to it. And now you kind of want to prove some condition on some fixed interval AB. So it's a very convoluted argument, but let's just see how we can do it. So the thing is, now we have R as an irrational number, right? R is irrational. And if I consider the set AR plus B, where A and B are rational, So in other words, we are taking the linear combination of R and 1, but the coefficients must be rational. Well, this is of course dense in R as well, because the set of rational numbers is dense. We're now adding some irrational number to the set. But the thing is, for any A, there exists B such that AR plus B is inside AB. Hang on. I should not use A and B. I already used that in the interval notation. Let's say QR and Q prime. So for any rational Q, I can choose this leftover term Q prime so that the number we obtain can be adjusted to be in this interval. That should make sense, right? It should directly come from the density argument, because you can just locate. Let's say we have R times, let's say 10,000, right? Then we get a very large number. But then we can just adjust it with some suitable rational, so that this new number comes back to this interval itself. This is obvious from density. And I claim that if I take this image, so the function of QR plus Q prime, I will get something very bizarre. Okay, so how do we do this? First of all, we should probably mention that our main equation was fx plus y equals fx plus fy, right? And we also managed to prove that fx1 plus ... I mean, I'll just write as a sum, fxi. So this actually means that we can take, let's say, a rational number times x, where x can be real. This should actually be qfx. Even though q is not an integer, it can be a rational number. Why? We can just do the same argument by multiplying by integers. So if we are multiplying x by a rational number, we can pull the rational number out of the function. If anyone's in doubt or have any questions, please ask, and I'll immediately reply. But if we are fine, then you can ask anytime, by the way, not necessarily when I stop talking. You can just ask in the chat if you have any questions. So now we have a linear combination of R and 1. So this means this is Q times FR plus Q prime times F1, which is C. And okay, let's just write this as C times QR plus Q prime. Because this is what we should expect it to be, right? We should expect it to be CX. But then we have some leftover terms. This will be plus Q FR minus CR. So this is a junk that appears due to the reason that FR is not CR. If it were CR, then fx is still cx. But since fi is not CR, now we suddenly have this junk added to this predicted answer. And let's see what happens when we crank up Q. Because we know for every Q there is a Q prime, right? So if we take Q to go to infinity, then this whole function goes to infinity, right? Because FR minus CR is not zero. It is a finite number, which multiplied by a very large number gets very, very large. I mean, it can be negative infinity as well, if this is negative. And we also can let Q to go to minus infinity to go in the opposite direction. So that means this function can tend towards both ends, can tend to a very large number or a very large negative number. And therefore, we're done, because this number is always in the interval. But we managed to prove that it's very chaotic when we adjust Q to be very large in the positive or negative direction. Then this number F will go to some very chaotic direction. So it's kind of like this. If this is A and B, and this is the y-axis and whatever, then the numbers, there are some very weird points where the image just suddenly blasts off to infinity and negative infinity as well. And then there's of course the rational numbers. So very chaotic function. And so we're done, because we managed to prove that if FR is not CR for some R, then on this interval, F is unbounded. It can be any arbitrarily large number. I'll give you guys a few seconds to digest this. Any questions so far? Any questions or requiring me to repeat any part of this proof? Please tell me. If anyone understands, please react something in the chat, because this is notably an even harder proof from the previous one. Okay, so it works mainly because there exists Q prime, right? Yes. So it is due to the fact that the set of rational numbers is dense in R. So given any Q, however large or however negatively large it is, we can still adjust it so that QR plus Q prime goes back into that interval. And in that case, we can, then we can get the result. So this is nice. This is very nice, because this is a very loose condition. That means if we find some condition like that, we can directly say that fx is cx. So this is the second case. And the third case, which is kind of an easy case after we prove the second one. So the third case, just put it to 3. The third case is kind of a subset of the second case. So F is monotone on some interval AB. And of course, we want the interval to be non-trivial again. So A is less than B. We don't want an interval where it's 1, 1, and then your interval just contains one number. So if F is monotone on some interval AB, so monotone means it's either increasing or decreasing. So anyone can see why this is just an immediate consequence of the second case? Well, my writings, some are quite big, some are quite small. Anyone can see why the third case is a subset of the second case? Okay, so someone said because it is bounded by the values at both sides. Yes, so you have A and B, you want this function to be monotone. Let's say it's increasing, that means if it's increasing, that means it's bounded from below by FA. If it's decreasing, it is bounded from above by FA. So either way, there is some upper bound or lower bound. So we just come back to the second case. So this is obvious from 2. Okay, so I mean, there are probably other conditions that allow you to conclude fx equals cx. Like for example, someone also introduced just now, if the function is continuous at some point instead of everywhere, so a very strong a much stronger condition. If f is continuous at some single point, I think it will still imply that fx equals cx, but we'll not prove that. Let's not prove that. So these 3 conditions are more of the famous ones. So these are sufficient conditions, but not necessarily necessary. Okay, so that ends our case study of Cauchy equations. But I would like to add some additional info. In particular, what if we don't have any conditions? So is there a general way of writing f solving the Cauchy equation? If we are just given nothing, we just know fx equals cx for rational numbers. But this section will be very advanced. It will just take probably a few minutes because I don't want to delve into this. It's just a very quick introduction. So what if no conditions are given? And probably it will never appear in Olympiad level. But sometimes if you know this fact, it kind of gives you a way of thinking. Like if you're given multiple conditions and then if you know what the general solution is, you can try to just plug in that general solution and then see what went wrong that doesn't allow you to conclude fx equals cx. So let's just talk about this case. What if no conditions are given at all? I mean, apart from the actual Cauchy equation. So is there a general way? Is there a general solution? General solution to the Cauchy equation. So here is where we first have to familiarize ourselves with this property. So f, again, just now we proved that f qx, where q is rational, but x is any real number. This is just equals to qfx. This was proven just now. So that means given any linear combination with rational coefficients, well, finite linear combination, we can just split it into qf1, q1 f x1 plus q2 f x2, and so on. So remember this property. This is true for the Cauchy equation in general, and it's also not hard to prove because we just proved it just now. So let this sink into your mind because it will be very important. So given any linear combination of x1 to xn, we can do this kind of thing. And someone gave an idea just now, I forgot who, but someone said, can we just assign a new number to f pi? And here is what we're going to do. So first of all, can we have some set of real numbers such that, let's say x1, x2, dot, 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 so that every real number can be uniquely written. So does this set exist such that, in fact, I'll call them B. I'll call them B. And for those who know linear algebra, you probably know where I'm going. So B1, B2, does this set exist such that every real number can be expressed uniquely as, let's say, Q1 BI1, Q2 BI2, dot, 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 Qn BI n. Someone said it's the span. Yes. And in fact, a stronger condition, we want to see if there's a basis. It's okay if you don't know what basis means, but this is the definition of a basis. So does this set exist such that every real number can be expressed uniquely as a rational linear combination of a finite number of elements in that set? Oh, so someone said intuitively it seems no. So the thing is, apparently, again, it's a yes and no. But the no is due to how I write this set, B1, B2, B3. The answer is there exists such a set, but the set will not be countable. It will be uncountable, and so we are not allowed to write B1, B2, B3. But I will not prove this. The general form is such a theorem, which I'll just mention now, and I won't prove because it's going to be something to do with axiom of choice and something else. In fact, if anyone has read Evan Chen's notes, Evan Chen, the famous ex-IMO guy from USA, he has a handout called Monsters, and it's quite good. Basically, it's talking about the general form of Cauchy equation. So the theorem is every vector space has a basis. And now we're just looking at R, the set of real numbers, as a rational vector space as a rational vector space over Q. Sorry, as a vector space over Q. So there exists some basis. That means there exists some set. Okay. There exists some set B so there exists B alpha. So I'm not going to write B1, B2, B3 again because it's uncountable apparently for real numbers. So there exists this set B alpha such that every real number can be written uniquely as a finite Q linear combination of B alphas. And if that's the case, then we just assign some value to every single basis element here. Someone asked, should we specify that BI are linearly independent? We don't have to, because I have the word uniquely here. So this means it will be independent, right? Equivalent to saying every real number, meaning it spans, expressed uniquely, meaning it's linearly independent. But anyway, let's look at a simple case which doesn't require that theorem. Let's look at a simple case that doesn't require that theorem. So instead of looking at R, which is a very large set, let's look at the little set Q, and then I add this thing at the back. So this means the set A plus B square root 2, where A and B are rational. It's kind of like complex numbers, but now you don't have I, but instead you have a square root 2. And then your coefficients here are rational. So this is slightly bigger than Q, but of course less than R, right? Pi is not in this set, for example. But we just work the same way. We just assign F1 to be C1 and F square root 2 to be C2. Then in general, FA plus B square root 2 is AC plus BC2. Oh, sorry, AC1 plus BC2. And you can just check, this satisfies the Cauchy equation for Q squared 2. It satisfies the Q squared 2 version of Cauchy equation. So this is just if I use the terminology just now, this is just a vector space with two basis elements. So the first one is 1, the second one is square root 2. And let's say you can have Q and pi, and then you have 1 and pi. So here's a case where you have two basis elements, and every single number can be expressed uniquely as A plus B squared 2. And you can check that this is true. But here we're just jumping to the very final case where we just say R, and R has not only two basis elements, there is uncountably many basis elements, and then we just assign any number to each of the basis elements. Then we can get the general solution, and that is the general solution, because we kind of found out that we have to assign some numbers to the basis elements, and also by doing so we can solve the equation. And so it's a if and only if thing, and so this is the general solution. So the general solution is to assign F B alpha equals, let's say, some number C alpha, then F QI BI would be just the sum of QI CI. So this is the general solution if you are not given any conditions at all. So it depends on an uncountably many choices. So it exists, but impossible to write it out. Yes. So it exists, but it's kind of impossible to write it out. So, but I mean, you can write out some obvious ones. Like, let's say you can have F1 is let's say pi, let's say 3, and then f pi is 7. Or let's say we just be crazy and say, let's say e to the e or something, and then f square root 2 is 1, and then let's say f everything else is 0. Then such a assignment will also exist. So you can write some obvious ones, but normally it will be quite impossible to write a different number for every single basis element. Maybe you can, like FBA equals BA, but this will be a general solution, and I will not talk too much about it. But I can accept any questions for now. Any questions before we move on to, well, before we stray back to to Olympiad level? Oh, you have a question that is not related to maths. Okay. All right, so it's a personal question, right? So I'll just type the answer for you, because it's a quite a personal question. So okay, may I know if these notes will be sent in the WhatsApp? Yes, yes. So I send. Oh, you mean this whiteboard that I'm writing right now? Okay, yes, I will. I think I'll be able to send it to WhatsApp. I should be. It's a bit large. I'm not sure if I can save it. If I can save it, I will just send it to WhatsApp. Or else, actually I don't have to, because I'm recording the video now, and in the end, someone, probably Zafi or Ivan, will send some Google Drive link where you can access the video recordings, and then you can just refer to the video recordings. Well, I'm recording now, right? Yeah, okay. I'm recording now. So I'll just, okay. So any more questions? Any questions? I'll accept any questions. Okay, if not, then let's kind of go back to some Olympiad questions. And if you have the handout now, you can refer to a few exercises that I have there. So the first section is where I list out techniques, right? So I'll go through the techniques one by one and elaborate on what they mean, because I think some of them just are very vague as I read it in a very short sentence. And afterwards, you can move on to exercises. So let's see the techniques. The first technique is the obvious one. Given a functional equation, you want to try to plug in some nice numbers. So the first one is quite obvious. You just want to plug in. That's the only thing you can do, right, for your first step. And the second technique is to guess the answer. So guessing the answer, of course, it doesn't give you any extra points, but it will give you an intuition of where you should be heading in your proof. So sometimes you can see, oh, fx equals, let's say 2x plus 1 works, and somehow it's the only linear equation that works. Then you know, okay, so whatever you want to do, you want to head towards the direction fx equals 2x plus 1. And if possible, even you can say, let's say, let g be f minus 1 over 2. Then you kind of know, if I transform it and we manage to prove gx is x, then fx equals 2x plus 1, and so on and so forth. But of course, this technique doesn't always work, in particular for an IMO shortlist question. I forgot which year. I think it's the recent years, either 2018, 2019, 2020, or 2021. The functional equation has some very obvious guessable solutions, but it also has a solution fx equals the floor function of x over n, where n is any positive integer. And if you didn't see this solution coming, you're gonna be quite in trouble. So of course, guessing the answer doesn't usually work. In fact, for that IMO shortlist question, you have to kind of but normally you cannot just guess this answer from a given equation. But at the end, let's say you're doing your workings and suddenly you say you have to introduce some kind of floor function to generalize the answer. And yeah, and so it contains this family of functions, which is very surprising. So yeah, just a word of caution, you guessing the answer doesn't normally work. So the third one is, and probably the question just now I'm saying about the floor function is probably A6, A7 or A8 on the shortlist. So if you're interested, you can just find it out. Or if anyone knows, you can just tell you on the chat. If anyone read that problem before, fx equals floor. I mean, maybe it's not floor x over n, but there is a floor somewhere in that functional equation. Okay, so anyway, the third technique is making substitutions like gx equals fx plus 1, or anything related. So, or let's say fx minus f0, or something. So you want to transform it to some other new function that probably will simplify the functional equation. Yep, and the fourth one, in fact, these are not the only techniques, by the way. These are just some of the techniques that I can compile. So the fourth one, consider some special values. Consider, or let's say find f0, f1, f minus 1, or some other special value. And where you're really stuck, remember what we did in the vector space concept just now for Cauchy equation. If you're really stuck, assign a number to it. So if really stuck, assign some fixed number to them, or whatever, and see whether you can solve that fixed constant at the end, or in fact really the general solution has to be in terms of some set of constants that are free to define. If that makes sense. And in fact, there are many functional equations that are of this style. So you can have infinitely many solutions and you can adjust it by some parameters. So the fifth one is a very interesting technique. So it's called forced cancellation. Oops. Actually, I had a typo there. It should be forced cancellation. The past participle, of course. So this means you want to force Okay, I mean forced cancellation works. It's just I'm just telling you to force the cancellation. So if you're given, let's say, f something equals f something plus other stuff, sometimes you can force these two things to be equal. So for example, let's say it's like f x minus fy, and then equals fy plus blah 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 blah. Then what can we do to force these two terms to cancel? We can let, anyone wants to answer? What can we do to force these two things to go away? Let x equals fy. If you let x equals fy, then this will be f0 on the left, but on the right is fy. So it doesn't really cancel both terms. But of course, in the actual question, you can probably do that and find some extra info. But the point here is that I can try to delete these two by, let's say, taking x equals, yes, so someone said fy plus y. If I put x equals fy plus y, then these two terms become fy. And then we can very conveniently cross both terms out. And if this is a very simple expression, like very simple junk at the end, maybe you will get a very useful information, because now you have a bunch of f's away. And of course, you have to make sure you can do that. Like for example, if you have questions like let's say it's something like that. So fx minus y, and this is, I don't know, fx. Then I don't think you can force cancel these two. There is no way in knowing that there exists x and y such that fx minus y equals x. Unless you know some kind of surjectivity or injectivity that I will explain later. So sometimes you can force cancel. In fact, if you can force cancel, do it immediately first, in case you forget. So as just now you say x equals y plus fy. If someone read your proof and say, oh, this is a very sudden substitution, it's not because you know what you're really looking ahead, but because you just want to force two terms to cancel. So you have this very weird substitution. But that substitution, of course, stems from the fact that you want to cancel those two terms. Okay, so the sixth one, so injectivity and surjectivity. So outside terms, what do you mean? Okay, never mind. So in injective and surjective. So does anyone not know what an injection or surjection is? I mean, injective function and surjective function. Or anyone forgot what they are? In fact, I'll just explain it again, because probably someone has forgotten. So injective means for all possible cases where fx equals fy, it must follow that x equals y. In fact, the reverse direction is obviously true. It's true for any function. But being an injective function means if you have two images being equal, that means their objects or their inputs must be equal. So if these are the two domains and codomains, you cannot have something like that. You cannot have something like that. So different inputs must lead to different outputs. That is what we call an injective function. And for a surjective function, it means for all x that exists, fy equals x. So every single output in the codomain, has an input. So if you draw those two terms again, that means every single term here has some corresponding input. So there are no isolated points in the codomain. Okay, so someone said like normally you need outside point to improve. Yeah. So yes, exactly. I will explain that later. So these are the two definitions, and then if both of these conditions are true, then we call the function a bijection or a bijective function. So a bijection function for a finite case it looks very easy. For a finite case, it's just a one-to-one correspondence. So it's a matching. So if there's a bijection between two sets, then those two sets must have equal size or equal cardinality. Okay, so how do we see if a function is injective or surjective, and why is it useful? So how? So let's talk about the how first. So to prove injection, you normally want, as someone said in the chat room, some kind of outside term. So let's say, if you forgive me, I'll just use your example, the example you've given. So let's say fx plus fy plus fy equals x fy. Is this provable to be injective? Okay. I think this one can be. Something like that. Yes, okay. So wait, does this help? Let me see. Yep. So given this equation, I can prove to you that f must be injective, or else f is 0 everywhere. So let's see how we can do it. So first of all, this is a very important thing. So there is an isolated x here. The x here is not inside any function. Like if you look at everywhere else, the free variables are inside the constraint of the input of the function. But this x here is kind of isolated, it's outside. So focus on this x. And you want to prove that if fa equals fb, then a equals b, right? And you see there's f-axis everywhere here, except this one. So that means if fa is fb, I can probably get a equals b in the end by utilizing this isolated variable here. So first of all, let's just get rid of this term, because if this is 0, it's very troublesome, right? So we have two cases. If we have two cases, case 1, fy is 0 for all y. And in that case, that means that would be the solution in this case. So fx is 0 for all x. So case 2 is where ft is 0. So that exists ft is 0 for some t. Oh yeah, the upside down e means exists, by the way. So if that's the case, we can just plug in that t into the equation. Equals x ft. All right. Now, how do we prove? Let's say f. So we say fa equals fb. Then I prove that if I put x equals a and x equals b on the left hand side, it's the same thing. Why? Because fa plus ft plus fa. Since fa is fb, this is the same thing as fb plus ft plus fb, isn't it? So we can just swap a and b. I mean, we can just put in a and b on both sides and the left hand side will be the same. But according to the right hand side, where we have the isolated x, we managed to see that this is aft and this is bft. And since we force ft to be non-zero, which is why we separated the cases, we get that a equals b. And this is how you prove f is injective. So you utilize some variables that are isolated outside of the function. Of course, it's not necessarily a necessary thing that, I mean, not necessarily it's always like that. There are some functional equations where there are no isolated variables outside, but somehow you can manage to prove it's injective. So you have some other conditions that help you to do that. So those are quite rare and those are very hard as well. But normally, if you want to prove something is injective, make sure you focus on these naked variables which are outside the function. Okay, for surjective, how do you prove something is surjective? So if you want to prove something is surjective, then you just have to prove that you can rewrite the equation in some form like this. And on the right hand side is something that you can adjust to be any number. If you manage to write the equation like this, then you manage to prove it's surjective. So for example, let's say something like that, f x plus fy to the x times, I don't know, 2 to the fx, whatever. So a very, very complicated thing on the left hand side, doesn't matter. Let's say on the right hand side is something nice. Let's say x over 2 plus fy. Then notice, if I fix y, in fact, I can just simply just plug in y equals 0 or something. If I fix y, so I put f equals 0. So this is something blah, blah, blah in terms of x, doesn't matter. And this is x over 2 plus f0. And now look at this. The right-hand side here, I can adjust this to be any number I want by adjusting x. Because x is free, right? Again, you look at the free variables outside, you look at the naked variables again that are outside any function. And this function allows us to adjust the right-hand side to be any real number we want, or any number in the domain we want. But on the left-hand side is f something. That means for every single output, there is some input that allows this to be true. So this is how you can prove something is surjective. Okay, so again, if you have questions, please do ask. And I will happily answer. And if not, let's move on to the uses. So why is injectivity and surjectivity important? So injectivity, what does it allow you to do? it allows you to conclude from, let's say you rearranged and manipulated the equation to be something like f x y, let's say something like that, whatever, equals f y or something. Yes, let's say you have something like this. And if you previously proved that f is injective, you can be very happy. Why? Because whenever you have injective functions, you can cross out the f's. That's exactly what injectivity means. If fa equals fb, then a equals b. So you can cross out f's if f is injective. That is what many people get mistaken about. They just cross out f without proving f is injective. You can only cross out f if f is injective. So if you cross that out, we get x fy equals y. And of course, this doesn't hold for any function. There is no such function. There's no such function that allows this to be true. But let's say you have, let's say, I don't know, let's say fy. Then you can get fy equals y. So injectivity, the use is that you can cross out f's. And surjectivity allows you to let, let's say, f a be any number you want. So you just pick, let's say, -1 or +1. So let's say you have a functional equation where you really want one term to be some number to simplify the whole equation. But that term is inside an f. But once you prove that f is surjective, you can let f, whatever that is, equals a number you want, and you can simplify the equation even further. So these are the main importance of injectivity and surjectivity. So, right, the next one is a very brief one. So odd or even. Is that the seventh one? That's the seventh one. Yep. Wow, it's very ugly. Seven. So odd or even. Of course, this is a very minor property. Sometimes it's quite useful. So an odd function is where fx, well, minus fx equals f minus x. And an even function is where fx equals f minus x. So you can imagine the symmetry in the graph. It's very simple work to do. I'll not describe it geometrically. But sometimes you can try to prove something is odd or even. That means you just have to focus on x more than or equal to 0 throughout your whole proof, because you already know this relation that relates the positive and negative numbers. So you can just focus on some half plane of real numbers if you manage to prove something is odd or even. And the eighth case is something that can be very easily forgotten. So you want to study what happens when some hypothetical scenario is true. So you're not sure if the hypothetical scenario works or exists, but you can try and see, oh, let's say something is true, and see whatever happens after it. Maybe whatever happens after it is that you get a contradiction. That means you gain one information, which is that hypothetical scenario cannot be true at all, right? So this hypothetical scenario can be, let's say, f some number equals 0 maybe, or f some number equals itself. That's called a fixed point. Or maybe some other conditions that I can't think about. Let's say ft equals 1 over t or something. Or maybe even ft is more than 0. If you prove a contradiction from it, then you know that ft is less than or equal to 0 for all t. If you cannot manage to prove a contradiction, it's fine. Maybe afterwards you can find some case where your hypothetical scenario can be true. And of course, thinking about the hypothetical scenario will be quite hard. You have to cater to the problem itself. And of course, the 9th one, the pointwise trap. This is again a very common fallacy, a very common mistake that are made by students. Let's say I'll give you a very simple functional equation, which is fx squared equals fx for all x, of course. So you might say, okay, let's cancel off. I mean, let's say you don't want to cancel off. Let's say you factorize, so you get fx. But whatever you do, you kind of know that the final thing is fx is 0 or 1, right? It's 0 or 1. Some would say that fx is the constant function 0 or the constant function 1. And does anyone see the problem in that statement? So, two solutions. Fx is 0 and fx is 1. It may be 0. Yes, so someone answered it. It may be 0 for some values of x and then 1 for others. So notice this statement here is fx equals 0 or 1 for all x. This is not the same. This is not the same. Not the same as fx is 0 for all x. Or fx is 1 for all x. Or sometimes you get fx equals 1 or x squared, maybe. Remember the pointwise trap. It is for every point, it can be one of the two choices. But it is not one of the two choices for every single point. So please digest this, is very important. So you can have other solutions. There's not just two solutions. In fact, there are infinitely many solutions. Let's say fx equals 0 when x is rational. Again, a very chaotic function. 1 when x is irrational. Well, this function also works, and many other will work. So what happens when you have this kind of condition? Well, either you are not given any other condition to which you must give the very general solution, or sometimes you can say, let's say fa is 0 and fb is 1, and then plug these two back into the original equation and get some contradiction. So get some contradiction where it must be either all 0 or all 1 by doing some sort of substitution like that. Of course, for the given equation that I gave you just now, this one here, this is the only thing you are given, so there are infinitely many solutions in every form that you like. But let's say you're given a very long equation and then this is your result instead. Then you have to plug back in and see whether it is possible for 2 points to have the same, to have different outputs. Of course, it doesn't just work for 0 or 1. It can be, let's say, 0 or x squared, or other things. Well, depends again. So that wraps up the techniques that I know. If anyone has any more techniques that you want to share, you can type it in the chat if you want. I will be very happy to add it to the list here. Exploiting symmetry. Yes, exploiting symmetry can also be a very good technique. Okay, so I'll just about the 10th one. Exploiting symmetry. Exploiting symmetry, which is a technique kindly given by Mr. Evan Lim or Evan Lim. I'm not sure how to pronounce it. So exploiting symmetry. Let's say you have a equation, and on the left-hand side of the equation, it is symmetric. Let's say fxy, fx to the x plus fy to the y. Very symmetric function. And on the left-hand side, you have, let's say, some not symmetric function. Let's say fx minus y plus y. Then you know if we swap x and y, the left-hand side won't change, but the right-hand side will. And if we swap, they must be equal because they are both equal to the left-hand side. So there will be fy minus x plus x. So whatever this is, you didn't even care. You get this new condition that you have. And is it useful? Maybe. Like from here, you can say fx equals f minus x plus x and so on. But of course, we need other information to solve this. So that's exploiting symmetry. Any other ones? And by the way, for the second point about guessing solutions, you can try to plug in, let's say, ax plus b or ax squared plus bx plus c, or some other test function that you can test and see whether you can generate some nice solutions. Okay, if that's all, then we can move on to the problems. We can move on to the problems. So let's do the first one. Find all continuous functions. So here they already tell you it's continuous. So f satisfying fx plus y equals fx fy. And it's R to R. So this looks very familiar to the Cauchy equation, right? Except the fact that instead of adding on the right-hand side, you multiply. Whenever you add on the inside, you multiply on the outside. Can we transform this back into some Cauchy looking equation? In fact, this is a very nice equation. It's like it's what group theorists would call a homomorphism. But yeah, there's just a fancy name for it. It's a plus. Yeah, never mind. It's a homomorphism. But anyone has an idea how to transform this into a Cauchy function? So how do we split? How do we force the product of two terms to suddenly become the sum of two terms by applying some kind of operation to it. We need to define a new function, right? Yep, and how would you define the new function? F0 is 0. Is it? F0 is not 0, right? Oh, okay, F0 can be 0 or 1, right? F0. Because F0 is F0 squared. Yeah, can be 0 or 1. If it's 0, it's the easy case. Because I just put y is 0, then fx is 0 for all x. Okay, so the first information we have is F0 equals 1. And by induction. Okay, yeah, so you want to follow the Cauchy. Sure, so nice. You don't have to transform it into a Cauchy equation. You can just directly solve it by induction. That's also fine. So here, we can imitate the Cauchy equation and generalize to n variables, x1 plus x2. I'll just write a sum notation. Sum x I equals the product of fxi. So in f0 is 1 and f, again, we don't know what f1 is, but I think it will depend. Well, the final solution will depend on f1. So let's let f1 be c again, because why not? So now by induction, we should get fn to be c to the power of n for natural numbers n. For natural numbers n. And if you want, say, the inverses, so f0 is actually just fx, f minus x. So f minus x is 1 over fx. So we just have to focus on the positive values of x, the positive inputs. So n is that. And now how do we go on to the rationals? The rationals. If we do the rational numbers, well, same thing, right? Let's say 1 over n plus 1 over n dot 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 plus 1 over n equals this thing to the power of n. This is 1. Wait, is it 1? Yeah. So sorry, f1 is c, sorry. So this is true. Now here comes one information. So when n is 2, this implies c is greater than or equal to 0, right? Because it's a square. So now, since c is greater than or equal to 0, we can say fn, f1 over n, must be c to the 1 over n. But again, minor detail, it can be plus or minus. I mean, it depends on whether n is even, right? If n is odd, then we can say for sure that it's equals to the n foot of c. So if n is odd, but for even cases, how can we be sure that it's it must be the even case. Well, let's say we just focus on n is odd. Then we know f m over n is c to the m over n again. So again, where n is odd. Can we first look at the even denominators case? Let's just focus on f half. So f half could or could not be square root 2, square root c, or I'll just put in power notation, or c to the minus 1/2. Oh, sorry, minus c to the half. Minus c to the half. And see whether that yeah. So yeah. So again, I think it has to be continuous. I mean, it must be continuous, and I think this has something to do with making it not continuous afterwards. So if it's minus c to the half, if it's minus c to the half, then what happens? Can a rational number be approximated by a sequence of rational numbers with odd denominators? Yes, yes, definitely. So let's just ignore f half. Ignore f half. In fact, for any real number, we can absolutely find some P1 over Q1, so rational numbers basically, that converge to R. Yeah, so someone said the correct thing. So we just ignore the even case because odd denominator rationals are also dense in R. Yes, that's exactly what I'm trying to use here. So even we kind of ignore the even ones, but the odd denominator rationals, of course, they are also dense in R as well. Because again, you can just pick a very large odd number as the denominator instead. So then we're done. Then by continuity, we're done. So we find that this converges to c to the r. So it is always c to the r. So fx is c to the x, where c is a fixed non-negative number. Yeah, I didn't complete this sentence, sorry. These must all be odd. And of course, these are all integers. Okay, in fact, I will need to restart the whiteboard because the thing is, if my whiteboard becomes too full, it will become very laggy, which I think you've noticed. So I'm gonna just delete the whiteboard and start a new one. I should be fine to delete it, right? Because I'm recording it, so I'll just upload the video afterwards. Okay. So nice. There is another solution for the question just now. which is a much quicker one. So the thing is, I will first transform this to a Cauchy equation first. So what we can do is to apply ln on both sides. I'll write this below here because there's some things we have to check before we can do so. So we apply ln on both sides. Then we get ln f x plus y equals ln f x. And you know the property for logarithms, you can just write this as ln fy plus ln fx. And now it's a Cauchy equation, and then we can just, of course, say that ln fx equals cx, and hence fx equals e to the cx, which is a to the x for some a. But anyone has any idea what I'm gonna add in between this space? What must we check to apply ln? In what cases can we apply ln? In what cases can we not apply a ln? Yes, you must prove it's positive, right? You must prove everything is positive. So, or we can put, yeah, we can, so we have to make sure everything is more than 0. So if we put 2x, x equals x, x equals y equals x, f2x equals fx squared, which is more than or equal to 0. So every single output is more than or equal to 0. If some number happens to be exactly 0, then fx plus u equals 0. That means fx is identically 0. So we have this case to make sure. We have to make sure, and indeed it's important. As you can see, it generated a new solution here. Fx equals 0 identically. And once we've thrown this out of the way, we can apply a ln and then get a to the x. But I think this one includes here, so we can just let a equals 0. So yeah. So in fact, this applies to a similar equation where we have fxy equals fx fy as well. You can try that as an exercise. I'll not repeat this problem. It's something similar. So let's try a second problem, but our class ends at 1, isn't it? So we only have 4 minutes left, probably not enough to discuss a problem. So I'm gonna open up to a Q&A session now. I mean, I know we have a lecture afterwards, but anything you wanna ask, related or unrelated to what I'm saying now, you can just freely put forward. Yeah, any questions? No questions at all. If you have no questions, you can probably look through the handout just for the last 3 minutes, so you can see what we've done just now. if someone interested what uncountable means, as I mentioned it about half an hour ago, uncountable means there is no bijection from that set to the set of natural numbers. In fact, there's a whole study of maths that focuses on the cardinalities of sets, infinite sets included. So there's something called ordinal theory, which is quite interesting if you look into it. So it characterizes all possible cardinalities of sets, infinite sets included. We don't just say, oh, this set's cardinality is infinite. In fact, there are quite a few infinities to describe the cardinality of an infinite set. So any countable set, we call it to have cardinality equal to aleph naught, if you're interested. And then you have aleph 1, aleph 2, aleph 3. These are all the uncountable sets. In fact, if you're interested in set theory and the very foundations of maths, you can look up probably any course material on set theory or ZFC set theory in particular. So it's Zermelo, Frankel, and the axiom of choice. So the cardinality of two infinite sets are equal if there exists a bijection between them. Yes, that's exactly the definition of cardinality. So we say two sets have equal cardinality, not necessarily infinite. Two sets have equal cardinality if and only if, because that's a definition, there is a bijection between them. And since there's a bijection between, let's say, the set of natural numbers and the set of rational numbers by the diagonal argument, so we say Q and N have the same cardinality. But apparently you cannot have a bijection between R and N. So R has a greater cardinality than N. And you can have other infinities as well. For example, the power set of any set, so the set of subsets of a set, must have greater cardinality than the set itself. So the cardinality of the power set of X, the power set is defined as the set of subsets of X. By all means, this must be greater than the cardinality of X. But the diagonal proof, the thing is, I don't think the diagonal proof necessarily works when X is uncountable itself. But this is also true for uncountable sets as well. So if you have R, you can apply power set, you get a greater cardinality and so on, even though they are all uncountable. So there's not just two infinities, countable and uncountable. There are infinitely many infinities, which they are all explained in ordinal theory. But of course, yeah, it's one now. So let's stop the class here. And I'll see you guys at 2:30, where we will move through the questions, go through the questions, and then see how we can apply those techniques in some very nice ways. So I'll stop the recording and